So continuing with radioactivity, we're going to look at deflection of alpha, beta, and gamma within an electric field. Now, what do we mean by deflection? We mean changing its original course of direction. So, for example, beta and alpha have charges. Alpha we know is positively charged and beta is negatively charged. Remember, alpha has a charge of +2 and beta has a charge of -1 since it's a fast-moving electron, and alpha is basically a helium nucleus. Now, because of this charge, they're going to deflect in both electric and magnetic fields. Now, very often students confuse electric and magnetic fields. They might behave in a very similar fashion, but they're not, I repeat, not the same thing. So if we have an alpha particle about to enter an electric field, what will happen is it will attract towards the negative because positive will be attracted towards the negative. Quite often in an exam, a student might draw this hitting the negative. Because the alpha is moving, it will deflect towards the negative, but not necessarily hit the negative. And in fact, it's very unlikely to hit the negative. Beta, on the other hand, is a fast-moving electron. It will deflect towards the positive, and again, it won't actually hit the positive plate. Gamma will go straight through. Why doesn't gamma deflect either side? Because gamma has no charge. Now, earlier we used paper, aluminium, and lead to detect whether radiation was alpha, beta, and gamma. But technically, you could take a Geiger-Müller tube, kind of take it close to the positive plate, and if you pick up radiation, you should understand that it is beta because negative is attracted to positive. Likewise, if I brought the Geiger-Müller tube down towards the negative and I picked up a reading, then surely it is alpha because alpha will be attracted towards the negative. And if I left it in the middle, then I hope you understand the radiation you would be picking up is gamma because gamma has no charge and it would not deflect. So here we are again, alpha going towards negative, beta going towards the positive, gamma not deviating in the slightest, and here are all three. Now, although it doesn't look like it, beta will deflect a lot more than alpha. In other words, it will bend up more than alpha bends down. Why? Well, alpha is a nucleus. Compared to an electron, it's much bigger. Therefore, the beta particle is much smaller. So the smaller particle will deflect much more than the bigger particle. Deflection in a magnetic field. This is based on Fleming's left-hand rule, where your thumb, your first finger, and your middle finger are all perpendicular to one another. They are all at right angles. So, how does this work? Well, basically, this Fleming's left-hand rule is based on conventional current. Conventional current goes from positive to negative. Now, we now know electrons don't actually go from positive to negative. They go from negative to positive. But back then, these rules were made up based on this one minor wrong fact. The thing is, the rules still work regardless. So there is no real need to worry about anything. So in this example that we're seeing here on the PowerPoint, it says the magnetic field is into the page. So my first finger, the knuckle is north and the tip of the finger is south, and I'm pointing it directly at you or directly at my computer screen. Gamma will go straight through. Why will gamma go straight through? Well, gamma has no charge. Alpha will go up the way. How does this work? Well, the magnetic field is into the page or into my computer screen, and the middle finger was going from left to right, which is what the alpha particle was doing. Which way is my thumb pointing? Which is force? It's pointing up the way. In order to do Fleming's left-hand rule questions, you will always be given two things, and you need to figure out the third. It's a bit like using a formula. The key, however, is to keep your fingers at right angles to one another. What I see a lot is students changing their fingers, moving them around. They must stay at right angles. Look, right angle there, right angle there. My fingers are always perpendicular to one another. It's like a key. The key, once it's in place, the fingers don't move. The only thing that moves is your wrist. Or if you find yourself doing anything awkward in the exam, turn the paper upside down. If you didn't understand that, we will be covering it in more depth in the electricity topic. Why does beta go down the way? Well, my magnetic field is into the page again. It looks like the beta is going from left to right, which it is, but according to Fleming, his rule wasn't based on electrons, it was based on conventional current. It was based on from positive to negative. So basically what you must do is flip the middle finger the other way. My magnet is still into the page. According to Fleming, electrons are kind of moving in the other direction, which means the actual force on the electron is down the way. So here we go. Here we've got alpha going up the way. Please do note that the deflection in this PowerPoint is exaggerated. It's a little too extreme. You get beta that goes down the way. Again, that is way too extreme when it comes to deflection. And we have gamma that does nothing. It goes straight through because it has no charge. Here are all three together. Alpha goes up, beta goes down, and gamma does nothing because it has no charge. You figure this out using Fleming's left-hand rule. Radioactive decay. For the purposes of the syllabus, you need to know about alpha and beta decay. Gamma is not so important for the IG because it has no mass. So, what happens during radioactive decay? This is when an unstable nucleus, as mentioned earlier from the bottom two rows of the periodic table in general, breaks up and forms something else. Now, if it's alpha decay, what will happen is this nucleus, for example, in this case, a mercurium, if I've pronounced it correctly, will decay to form a brand new element and give off an alpha particle. So, this unstable nucleus gives off an alpha particle and turns into something else. Your job is to remember that alpha has a mass number of 4, an atomic number of 2, and you have to remember the symbol. Why? Because basically, in the exam, they're likely to give you all of this, and they're likely to give you the letters over here. What they're not likely to give you is all of the alpha and the numbers over here. Your job, quite simply, is to make sure the numbers on the left and the numbers on the right-hand side match up. In other words, the equations are balanced in terms of mass numbers and atomic numbers. 241 minus 4 is 237. 95 minus 2 is 93. Beta decay. A neutron changes into a proton and an electron. The electron leaves the nucleus as a fast-moving beta particle. So this is one that students find a little harder to understand. I've said before that in the nucleus there is no electrons, and that still remains the case. However, in beta decay, a neutron changes into a proton and a fast-moving electron, which is ejected as a beta particle. So the nucleon number will be unchanged, but the proton number goes up by 1, which in essence means the neutron number goes down by 1. So here we've got an unstable nucleus. It's going to decay with beta emission. Again, it will form a new element, but the key is you have to remember what beta looks like. Mass number 0, atomic number -1, and you have to remember the symbol. Now, what will happen is you will be given all of this. You'll be given the symbol here. You won't be given any of this or the numbers on the left. So what do? Well, basically, like before, you balance the equations. 90 minus 0 is quite simply 90. And 38, now be careful, minus 1 is 39. If you didn't understand that, let's work backwards. 90 minus 0, 90. 39 minus 1, 38. Remember, my goal is to balance the equations. That's what I'm trying to do. So, alpha, 4,2 helium nucleus, mass number 4, atomic number 2. Beta, mass number 0, atomic number -1, effectively, and it has a negative charge. Gamma has no charge. Now, something else that students find quite difficult to understand, radioactive decay is a completely random process. I cannot tell you which one of these nuclei or atoms is going to emit radiation. It's impossible for me to tell. Why? Because the entire process is random. No amount of raising the temperature, increasing the pressure, surface area, trying to do anything to speed up the reaction is going to do anything. The actual process itself is random. Radioactive decay is random. You'll not be able to tell which nucleus will decay next.